Thank you, Di. And welcome everyone. I'm very impressed by everyone's attendance at this time of the year, but it does reflect the caliber of the speaker that we have. So thanks everyone. So my name is Fern Terrace-Prestalt. I'm a professor of health economics. I also work at UNAIDS as a health economist leading their cost and efficiency work. And I'm a co-convener of the Health Preference Research Special Interest Group. This is the fifth webinar in our jointly run seminar with the International Academy for Health Preference Research and the journal The Patient, who have been running a series of good practice in health preference research. So thank you all for joining. So today's webinar, we have the great honor of having Professor Reid Johnson join us. He's going to talk about Introduction to Quantitative Analysis of Choice Data. What can discrete choice experiments tell us about patient preferences? This is one of the more recent papers that he has produced, but he has been producing for the past 3 decades health preference research in healthcare. He told me earlier that he was only 6 months after one of our colleagues, Mandy Ryan, which some of you may also know. And in asking about what some of his most important work or the work that he thinks most fondly of, it's his work around ensuring writing how to submit health preference research to the FDA, the Federal Drug Administration, which really is in charge of the regulatory procedures for drugs. So really having an impact where health preference research impacts policy and implementation in people's lives. So without further ado, I'm going to hand you over to Reid. Over to you. You've also mentioned that if there are questions of clarification or we're a small group, so we can make it a more workshop style, feel free to put up your hand and ask questions along the way.
I'm pleased to be able to introduce you a little bit to quantitative analysis of choice data. I'm leaning very heavily on an article that I and 2 of my colleagues published last summer in The Patient. This is a part of this article is part of a series of practical applications that the journal The Patient is publishing. That'll eventually be collected in a special issue of the journal. So one feature of this article is that it contains supplementary material. And the supplementary material is the actual code that we used to estimate the models that are discussed in the paper, and instructions on how to run the models in both R and in Tchaikovsky's programs. I'm not going to spend any time on this. You can look up the article and download the materials, but just to emphasize that everything I show you today, you can reproduce yourself with the supplementary materials in the article. All right, we are focusing today on a specific kind of stated preference method, which is called the discrete choice experiment. I lost the battle years ago on what to call this. This was Jordan Louviere's term. I prefer just stated choice modeling or studies. I didn't like the lab brat implications of experiments, but whatever. It is experimental in the sense that we have complete control over how the data is generated. So I usually, when we run into problems with our data, I usually just point out to my friends that we have no one to blame but ourselves because we generated the data. So this approach is a way to simulate choices using constructed choice sets. And then the particular pattern of choices that we observe can be analyzed with statistical models to evaluate the relative importance of the various features that were shown in the choice sets. So the idea is that as people are comparing two different alternatives, they are implicitly assigning relative importance weights to the various features that they're being shown in order to determine which one has the greater utility. And I'm going to use utility today, not in the sense of health state utility, but in the way that utility is used throughout economics except in health, which is an indicator of welfare or well-being. So the quantitative preference weights tell us how much of one feature, say pain, people would trade off for something else, say cost. That is, all right, I would prefer to have less pain, but not at too much more cost. And we can determine exactly the amount of cost they would be willing to substitute for a change in pain. All right. Come on, not. Whoops. Sorry, I'm having a little trouble with my keys here. So here's an example. This is a study that is trying to understand the trade-offs that people are willing to make with regard to treatments for severe headache. So the features, we also call them attributes, include severe headaches per month, how many people had a heart attack in 10 years from taking the medicine, that is the risk of taking it, how you take it, mode of administration, and your personal cost, that is the cost to you that's not covered by some kind of insurance. And then, so what we ask is that people look at these two alternatives, and if these were the only alternatives available to them, which medicine would they choose? Okay, and they complete, 8 to 12 of these.
Reed, I'm so sorry to interrupt.
Yeah.
I think your slides are not moving ahead. So most of us are seeing your first slide still, and they're not full screen.
Oh, that's not what I'm seeing.
Yeah, sorry about that.
Can you see this?
If you try to reshare again.
All right. So did you see this screen?
Now we're seeing your, but yeah, this is the first. Move forward. Yep. And now make it make it display mode. Yes, now we're seeing your slides moving.
Okay, now you didn't see what I was saying about the task layout, is that right?
No.
Ah,
And we're not seeing them full screen. We're seeing your notes pages.
so what are you seeing now?
We're seeing your notes page example DC question format, but we're seeing it in editable mode rather than full slideshow. You can also try presenting in Teams.
I've got two screens.
Yeah. So either swap
Yeah, let me swap it.
display or
Yeah.
present in Teams. You could try presenting it in Teams.
I'll just move it over to the other screen. Okay. How's that?
We can see it, but we still see your other slides as well.
You see other slides as well.
There, that, and now we're seeing your notes. Here now, just swap your display settings.
I just did.
In the middle, no, you're on the right track. In the middle, you see display settings, right up by your cursor. Show taskbar display settings. If we swap those around, right up on the top.
Up on the top. I'm seeing it okay.
Okay. Otherwise, we can see the slides. It's okay. Don't worry. They will move there. It's just not in display setting.
Right. If I move it over here, does that help?
No change.
No change.
It was better when you were displaying Teams, but it just had the wrong slide setting. It's okay. We can see.
I've never had this problem.
Don't worry. We can see start slideshow. If you go to start slideshow up on the left.
Oh, you see my note slides, right?
And not right now, no.
No?
We're not seeing the notes, no.
Do you see a full screen of the task layout?
We can almost. Okay, try stop presenting and share once more. We will get it. Apologies, everyone. We were having a nice conversation about Reed's extensive career, and we didn't test out the slides.
I thought we did, actually, with the moderator. Now what?
Okay.
All right, this is what I'm going to do. I'm going to stick on this.
Yeah.
Get rid of this.
We see your full slides. Yeah, that's fine.
Yes, let's do it that way.
Great.
Okay. All right, I'm sorry. We're going to hustle through this now. This is the task layout that I was talking about. We have attributes of severe headaches, risk, mode of administration, personal cost. Individuals look at these two alternatives, medicine A and B. We ask them, if these are the only alternatives available to you, which would you choose? That gives us the statistical information we need. So this is the attribute table. So attribute is the feature. Levels are the values that each of the attributes can take. So we will, in the choice task, they will see efficacy, that is headaches per month, as either 0, 1, or 3 headaches per month. Risk is either 0 or 1 or 3%. Mode of administration, infusion, injection, tablet, and 3 levels of cost. All right, this is what the data set looks like. No one ever explains this to people. But the answers to the choice questions look like this when you lay out the data. So in this case, we have 5 questions. There are 2 alternatives each. So row 1 is the first alternative, row 2 is the second alternative. So there are 10 rows for respondent number 1, alternative 1 and alternative 2. And there's an indicator of which one they chose. In this, for the first question, they chose alternative 2. They chose alternative 2 for the second question as well, but they chose alternative 1 for the third question. And here are the attributes that were shown to them. The first one, the one that they picked, alternative 2 for had 1 headache, the other alternative 1 had 0, had 3% risk, and was injection with a cost of 50. Now, age never changes because age is attached to this ID. So it doesn't really matter which questions they saw, it's always the same age. So respondent number 2 was age 60. And respondent number 2 is going to see different questions, not necessarily the same ones as respondent number 1 did. Okay, skip over this. This is kind of basic statistics stuff. So once we have the data laid out, we need to decide, since these are categorical variables, we could estimate these as continuous, but I'm going to show you why that's a bad idea. So everyone's familiar with dummy coding. So if we set 0 for 3 headaches, which is the worst value, then no headache would be 1, and one headache would be coded as 1, 0, and one headache would be coded as 0, 1, and 3 headaches would be coded as 0, 0. Many preference researchers prefer effect coding. Effect coding just changes what the reference value is, and it sets it to the mean effect. So when you sum over, so 0 now is the mean effect, and so anything less than, so the mean effect would be 1 headache. I don't know, it'd be 2.5 headaches or whatever. In any case, if you sum these in each column, it will always sum to 0. So you can recover. So if you have this 1, 0, 0, 1, that's 1, 0, 0, 1, the omitted category is coded as -1. That is, it's minus the sum of the other 2 levels. And if it's minus the sum of those other 2 levels, it's going to sum to 0. We'll show you in a minute what the advantages are of effect coding. All right, I'm going to take a look today at 3 different model specifications. But all of the models will be based on this particular statistical model, which is we'll define the utility of alternative H as the attribute level. You have all of the attribute levels that are shown in that attribute. The probability of choosing A. I have a note to myself. There's supposed to be, well, the probability of choosing A is the exponentiated utility of AH divided by the sum of the exponentiated utilities of both of the alternatives, plus some error term. We don't assume that people always accurately answer our questions. So this defines relationships between choice patterns and variables. We need to be able to link the preference estimates that we get to this underlying conceptual framework. So for a linear additive model, all we do is, so for the 2 alternatives that I showed you a couple of slides earlier, remember the headache, it was 1 headache versus 3 headaches. The risk was 3% versus 1%. It was infusion versus pill, and $150 versus $50 cost. We multiply each of these attribute levels by its own beta coefficient, and that gives us the utility of A and the utility of B. This is called a main effects model. The utility is a linear function of the individual attribute levels. So the betas are going to tell us the relative value of one versus 2 or 3, or I'm sorry, 0 or 3. When I review manuscripts, I sometimes see that people have inserted a constant term here before this equation. The problem with that is that all it tells you is whether people prefer A over B, regardless of what the attribute levels are. If that's significant, then they're not paying enough, the respondent is not paying any attention to the actual attributes. So we usually suppress that, or maybe check it as a validity test. Now, continuous variables can be modeled linearly or linearly. If you are going to use a linear assumption, then you better first estimate a categorical model and demonstrate with a linearity test that the data actually is, that a linear model is actually appropriate. All right. Here's an example of the problem of just assuming a linear probability. We estimated a categorical, this is for 10-year mortality risk, and here and the vertical axis is the preference weight for these. This is a very old study of mine. Here are the 3 categorical estimates using, doesn't really matter, either effect coding or dummy coding. And then we estimated a weighted probability function. And you see that the weighted probability function traces the relationship among the nonlinearity among the categorical variables. If we had assumed a linear probability, then we would have gotten this. And we would have, if you had done this test, you would have rejected the linear assumption. All right, attribute interactions. The problem with a main effects model is that there's logical interdependencies among these things, specifically for pain intensity and duration. People can't tell you how important intensity of the pain is, or the frequency of the pain, unless they tell you the duration of it. We, in this particular study, we told them that we standardized all of the headaches had the same duration, and they had the same intensity. All that varied was the frequency. If you're going to include this kind of interdependence, it has to be, this particular study, this particular presentation is not dealing with experimental design, but the experimental design was the rules that were used to construct the questions. If you anticipate that you're going to need an interaction, then the experimental design has to include patterns that will allow you to recover that interaction. This particular experimental design did not do that. Yeah, one consequence of estimating interactions is that means that you're going to have more choice questions to estimate the same statistical accuracy. One problem with categorical variables is that interactions can end up being extremely complicated. And my advice usually is to either use a linear interaction or a nonlinear continuous specification for, that is, use some sort of, we tend to use what's called a Box-Cox transformation for a continuous nonlinear model. All right, we have 3 options here for estimation method. The conditional multinomial logit is basically the OLS equivalent, ordinary least squares regression equivalent for discrete dependent variables. It is a very simple model that requires very strong assumptions. So the supplementary material gives you a program to estimate the headache data, and for a conditional logit, or in some software calls it multinomial logit, the programs included in the supplementary materials will give you these estimates, and these are coded as effect coded. So you can see if you take the negative sum of 1.6 and 0.1, you get minus 1.7. So the nice thing about this is that you get a parameter estimate for everything. You don't have all of the attributes sharing a common zero. So that it just makes it easier in secondary analysis when you have an actual attribute level estimate for all the attributes. We're estimating cost as continuous. It is inherently continuous, and we kind of assume that the marginal value is going to be constant. All right. So checking quickly, we got sensible results here. People preferred 0. 0 has a bigger utility value to 1 headache, and 3 headaches is strongly. Remember, 0 is the mean effect. It isn't so much that this negative value. So, for example, yeah. In this case, infusion injection are both less than the mean effect. So when you take the negative sum of 0.25 and minus 0.11, you get minus 1.4. All right. Here's comparing effect coding versus dummy coding. These are the effect coded estimates that I just showed you, and you see that they're centered on 0. But look what happens here. If I take this value for 3 headaches and move it down to 0, or move it up to 0, then we get exactly the same shape. We're recovering exactly the same statistical information. We're just normalizing. We're just defining 0 differently. And likewise here for risk, if I take 0 risk and I move it to the omitted category, then we get exactly the same line, and so on. Okay, so there is no statistical reason for choosing effect coding or dummy coding. If you're comfortable with the dummy coding because that's what you got in your statistics course, that's fine. Now, let's compare something called mixed logit with conditional logit. All right, so again, I'm using the dummy coded estimates here for the conditional logit. These are what I just showed you in the previous. Sorry, conditional logit as the blue that I just showed you in the previous slide. Now, mixed logit relaxes the assumption that everybody has the same preferences. It estimates both a mean value and a standard deviation for each of the relative importance weights. So we can allow each of those importance weights to vary across individuals. And the standard deviation gives us an indication of the degree of, we can call it the degree of consensus there is about the relative importance of this attribute level in our data, in this sample of respondents. But look what happens when we take into account unobserved taste heterogeneity, is what we call it. When we take into account the possibility that people don't all have exactly the same preferences, we get different willingness to pay values, significantly different. That is, you get lower willingness to pay for headache, to go from zero headaches to to go from 3 headaches to 0 headaches, people are willing to pay about call it $130, say, and it's more like $180 for Mixlogic. Moreover, they're willing to pay more for to avoid the risk. And we get a qualitatively different result here for mode of administration. For conditional logit, there is no difference between injection and infusion, but there is a statistically significant difference in the mixed logit model between injection and infusion. So we always estimate a conditional logit model first because it's easy. Mixed logits can take more time and are a little more challenging, but it is possible that you'll get this kind of result. We sometimes get very similar results on mixed logit, and sometimes we get very different ones. All right. Latent class analysis. Oh, I love latent class analysis. Latent class analysis says, you know, what if there are different groups of people who have similar preferences? And so the analysis of this particular data set shows that there are 2 very different classes. There is a risk tolerant class. You see here that the overall importance of this of the risk is the length of this line. It's basically the utility change between 0 and 3%. And you see that class 2 is very that suffers a very large decrease in utility as the risk increases, whereas class 1 doesn't suffer much of a much less decrease in risk as a result of the risk. And similarly, it works the opposite way, for class 1. They really care about efficacy, not so much about efficacy for class 2. They're more worried about the risk. There's not much difference here in mode of administration, but there are clear differences here in people's risk tolerance. What happens, of course, is we're averaging these 2 very dissimilar groups of people, and in the conditional logit, we're taking the average person, and there is no average person. There are risk tolerant people and there are risk intolerant people. There's no person that's sort of average risk tolerant in this sample. Not taking into account this clustering effect can result in very different results. All right. There is no consensus on a preferred package. Let me give you a little advice here. If you work in SAS, then I would say just stay in SAS. There is a very good library of procedures to do all of these different kinds of specifications, that model types that I've discussed. Stata also has a set of procedures for doing all these things. There are some limitations on what Stata can do with mixed logit. If you have too many parameters, I think there are a limited number of parameters that you can estimate as mixed, but you don't have to estimate all your parameters as mixed logit. R has Stefan Hess's Apollo programs. It's a suite, the Apollo suite of DCE programs contains every imaginable thing you can do with choice data. Because it's programmed in R, you have access to all the details of the specification. If you work with R, I would say go absolutely directly to Stefan Hess's Apollo program. I'll give you the supplementary materials gives you a link to download. It's free, and Stefan Hess seems to spend all his evenings answering people's questions. I've sent there is a very active user website. I've sent him a couple of questions and he answers within 2 or 3 days. I don't know what else he does with his life, but it's a great service. There is in MATLAB, if you work with MATLAB at all, there is a program by a Polish economist, Mik Tchaikovsky. I really like Mik's programs. Once you set up the basic data and define all your variables, it will just go ahead and run 6 or 7 different specifications without doing any additional setup. And the MATLAB code is open code. Yeah, if I think working with R is, I'm not a real hardcore R user, but I do work with MATLAB. So I have provided a link to Tchaikovsky's MATLAB program and an example setup to run all of these models in MATLAB as well as in R. There is some commercial software, and Logit for a couple of decades was the kind of go-to program for estimating choice models. There are still people who like it very much. Sawtooth software is a DCE in a box. For beginners, it's for students, the cost is pretty reasonable. The commercial license is not so reasonable, I think. But if you're starting out, I would strongly advise you to get Sawtooth software. Sawtooth will do everything except the attribute table. You have to give it the attribute table. Then it will generate questions. It will collect the data. You can. They have a service that you can direct your respondents to the Sawtooth host, and it will collect the data and do the analysis for you. It will not write the manuscript, although I can spot someone who has used Sawtooth software immediately when I look at the manuscript. The problem with Sawtooth software is, as my old scoutmaster used to say, it's a useful tool but a dangerous toy. That is, you can run it, but that doesn't mean that you specified a model that made any sense, that you would understand how to interpret the results. There is a lot of concern nowadays about quality of data, which is a separate issue that we haven't addressed at all today. But like I say, there are people who use only Sawtooth, and they get smarter. Sawtooth also has an annual conference, and it has an enormous library of tutorials on various aspects of state preference research. It initially was designed to do commercial market research. And sometimes the terminology is a little different than what I learned, at least in econometrics. Then in our group, we use latent gold very heavily. Latent gold also is a software package that was originally developed for market research, but it is very, very sophisticated for doing latent class analysis. You can do conditional logit and mixed logit by just running a single class latent class model in latent gold. One thing that well, we have learned how to do a number of things with latent gold because it gives you a lot of control over how you define the classes. You can do latent class analysis in Sawtooth or in Logit or SAS data or R. But latent gold is sort of designed to do latent gold to do latent class analysis in a very sophisticated way. All right. The way you estimate your model matters. Not too surprising. Results can vary significantly and have huge implications for out-of-sample prediction. On the other hand, there's no one model that is the best approach. It depends on what your research objectives are, your sample size. If you have a small sample size, forget mixed logit. You just aren't going to have enough power to estimate, and to basically it doubles the number of parameters you have to estimate because you estimate both a mean and a standard deviation for each parameter. The more complicated the model is, the more attributes you have, the more levels you have in each attribute, places more statistical burden on the analysis. More complicated models just require more data. And so again, it's not going to be suitable for small samples. Mixed logit uses a simulation estimator. And that, if you have a lot of parameters that have to be estimated with mixed logit, it can take a long time. In R, for a sort of a typical study, a bit more complicated than the example that I used today, it can take, I would say 20 minutes to 40 minutes maybe to estimate one model. So that's a good reason to do conditional logit or multinomial logit first, so that you don't do sort of specification exploration in mixed logit. So begin with conditional logit and then progress to mixed logit or latent class models, depending on what your data can support, the amount of time you have, and what kinds of questions you want to answer. Now, I don't know, nobody interrupted me, but I'm going to get out of this.
Thank you very much.
All right.
That was fantastic. That was really helpful. I wish you'd been around giving this webinar when I was doing my PhD, because I know how long I went around in circles. And right after I'd gone around in many circles, the primer came out, choice modeling a primer, and that just made a huge world of difference to people who were starting off on choice models, because I couldn't figure out what to put where. And I think your intro has been really extremely useful. And I think that's why, and Logit was quite popular for, as you mentioned, in those early days.
Yeah. So what makes a huge difference is to have code You can listen to people talking about how to do this and that, but until you've got code to work with, you've got nothing.
Yeah.
So I'm hopeful that the code that we're provided in the patient's tutorial,
Mhm.
people will use and find useful. It's simulated data, so it's nice, clean data. It gives us the results that we wanted to show. You can't necessarily expect your own data will be as well behaved.
Yeah, definitely. And we have our first question in the chat. Remy, feel free to ask it and put on your camera if you'd like to introduce yourself. And as you do so, I'd just like to mention that the presentation will be online on the IHEA website, so anyone can watch it. No problem. Then in that case, I shall read it out for you. So Remy says, great presentation. Can you tell us a little more about the independence attributes assumption? Does their independence refer to the orthogonality between when creating sets, or is it really an independence of attributes between them in the head of people who pass?
Yeah, okay. This of course is a question that belongs in a different presentation, but I'm happy to respond to it. There is, I believe, a one of the patient tutorials covers experimental design. All right, so what we are trying to do, unlike what we call revealed preference data and other people call real data, is that everything is confounded. Everything moves with everything else. It's almost impossible to isolate effects. So the reason we call it an experiment is we have control over. And in the real world, there are a certain number of pain medications. They are what they are. They have the side effects that they have, and they have the cost. You have no control over it. And some of the things move together. But we can break those confounded effects apart and generate a synthetic choice where the attributes are shown in a way that they move independently of each other. That is, their correlation coefficient is 0. And that's what the questioner, what Remy means by orthogonal, is that, yeah, everything, every value of everything else appears with every value of one attribute appears with every other value of other attributes. Now that turns out that's an orthogonal design, and it has this nice property of everything being perfectly non-correlated. But it turns out that that kind of design is not very efficient. And so when you look at when you generate your experimental design using the experimental design software, you will be given a choice between an optimal design and an efficient design. An optimal design is orthogonal. An efficient design uses priors. You may have some priors about relative parameter sizes. And if you do, you can generate a design that's more efficient than an orthogonal design. Does that work, Remy? Okay. Really? All right.
Great.
I'm going to go back.
I have a question.
Oh, you have? Okay.
Yes. So you mentioned using MNL for to test your specification. How reliable is that as you move to other models? Because a lot of these other models are assuming there are some quite strong assumptions in MNL. And if you're testing your specification, maybe it doesn't hold once you're able to unpack some of the things.
Well, okay.
I like the idea.
This is my experience.
Mm-hmm.
MNL, multinomial logit, I prefer conditional logit because that's what McFadden called it. don't get me started. Multinomial logit as applied here. Every time I've used it gives you the same qualitative results.
Mhm.
So if you're just trying to explore specifications, just realized I didn't talk very much about covariate analysis. So the problem with covariates in state of preference results in analysis is, as I showed you, everybody has the same age, and it doesn't vary between the alternatives. So a choice between A and B tells you, by a 60-year-old person, tells you nothing about the effect of age. So you've got to interact age with the actual questions that the person answered, which means that you're going to multiply all those ages by 3 different levels. I mean, it's just intractable. But there are other things you can do in terms of specification. You can do split sample analysis, has its disadvantages. Or you can do latent class analysis using conditional logit. You can mix. What we like to do is do latent class analysis with this mixed logit inside of the latent classes. But latent class analysis very easily can estimate for a long list of covariates what the probability of a person of a given age has of being a member of each of those classes. And that can be extremely useful. You know, there may be systematically, we often find it, education, gender, disease experience can influence which latent class a person is likely to belong to.
So you just mentioned something that's quite interesting about the mixed logit latent class analysis. There are only a few papers out. Why do you think that's the case?
Because if it's hard, if it takes 40 minutes to get a one class model to work, if you've got 4 latent classes and 20 parameters, and I estimated. I've been working on evidence basis, so I generated an evidence base for inflammatory bowel disease. I have 10,000 observations. I had a mixed logit model, and yeah, I had 100 parameters to estimate. You're not going to get mixed logit. I would love to have done mixed. You can say, oh, but you have to assume, yeah. But
there are only a few out there. There are definitely only a few out there. It's fun. It's fun, but the added value. So
let me just be a little critical about mixed logit for a minute. Mixed logit has its own assumptions, and the common assumption is to assume that people's tastes are distributed normally. There is no conceptual or statistical reason to think that people have nicely, normally distributed differences in their tastes.
So you can specify exactly the distribution.
The normal distribution on the error term is based on the central limit theorem, but has nothing to do with people's behavior.
So in logit, you can specify it, but we have very little theory to base what other specification we should be using.
Oh, well, you don't need a lot of theory to know that the cost parameter can't be negative. Estimate a normal distribution with infinite support, a bunch of that tail is going to slop over into the negative quadrant. So first of all, you can say, no, normal will not work on a cost attribute. Or any other, it won't work on risk. Okay, it won't work on anything where we know that it's either positive or negative. But nevertheless, every manuscript I read is estimated a normal distribution.
So we have 2 more minutes before we need to wrap up. I'd love to hear a little bit more about your choice of models and policy use, because you did mention a bit about latent class, how you like them. Can you help us if we have different policy questions? Does that affect our choice of model?
We often work with physicians at Duke. And when they get interested in this kind of study, we do it with hundreds, sometimes thousands of patients. And they say, well, this is very interesting, but how can I use that with my own patients?
Mm-hmm.
And so we started doing latent class analysis and showing the latent class analysis to a physician and say, they would often say, if we had 3 classes or 2 classes, whatever it is, they would say, I know those patients. I see those patients. How can I figure out quickly which class those patients belong to? And what one of our current research projects is to figure out how we can ask patients 2 or 3 questions that will diagnose which latent class they belong to. So the physician, we diagnose their preferences. The physician says, oh, this person is risk averse. I'm not even going to talk about those really risky things. Let's focus on the things that they are likely to really be interested in. That's the clinical thing. That in terms of regulators, FDA would like to know what proportion of the patient population is risk averse, because they don't have to regulate those people. They regulate themselves. Those are people who just, once they see that long list of bad things that can happen to you, they're not going to go for it. But they would like to know what proportion of patients are likely to, what the uptake is likely to be, because that will give them a way to translate the clinical trial data into post-marketing results.
And Remy has a very good question about parameterizing models with DCEs. But I don't have your email, Remy, so if I can pop mine in if you want.
Just send me an email. It's reed.johnson@duke.edu.
Yeah.
I'd be happy to answer any other questions.
Yeah, and I've written actually a few papers on using DCEs to parameterize with some of our colleagues, Matt Quaife and mathematical modelers. So I'll try to capture this in my email. I think we're at the end. So this was fantastic. From a policy perspective, where I'm working now, where we look at differentiated delivery and really looking at service delivery for different patients, the latent class provides so much more data than the interpretability of mixed logit, really. Thank you very much. That was really extremely useful, and I know that this will be very well reviewed from clients, from people who can't attend today in Australia or around the globe. So I'm going to thank you for our last webinar in this series and our last webinar of the year. We will have new ones in the year. Thank you very much. We can all
organizing and shepherding this, Fern.
So Matt has been organizing. Matt Quaife has been organizing this series. I've been quietly listening in, and you have a many thanks from Lazarus and other people in the chat. Over and out.
Thank you. Thanks everyone for joining us today.
Bye.